This session, we will be learning about one of the applications of differential equations, which is Newton's law of cooling. So for Newton's law of cooling, the rate at which the temperature of a body changes is directly proportional to the difference in the temperature of the surrounding from the body itself. So for example, let's just use T as the temperature of the body at any time. T sub 0, Ts. Ts is the surrounding temperature or the outside temperature. So that means the standard form is here, dt with respect to T is proportional to the differences in the temperature between the body and the surrounding. So if we use this, for example, dt temperature with respect to time is K, proportionality constant, times the differences between the temperature of the body at any time and the temperature of the surroundings. What's going to happen is that you can separate this because this is variable separable. So far, do you understand up to here?
Yes, sir.
All right, and then this one is ln T minus T sub 0 is equal to KT plus ln C. So you might say, sir, why is it ln C? Why not just C? It's okay. You can, because you can put the here. What if the constant is with this? You place it with this. So it's an ln. So it doesn't really matter. So here, similar to what we've been doing in the composition, growth, and decay, you combine those terms. And then the KT stands alone. So this one, applying the laws of logarithms, this one becomes a quotient is equal to KT. And then we would want to remove the ln. So e raised to those. So that means the left side becomes T minus T sub 0 all over C is equal to e to the KT, or T minus T sub 0 is equal to C e to the KT. So you'll end up with this one. So take note that the one below, please take note of this. This one is your general solution. This one is the form of your general solution. And then we would want you to please take note of the following assumptions. In Newton's law of cooling, please take note that we cannot expect any chemical reactions because, when there is chemical reaction, the reaction releases heat or absorbs heat. That's why you can't expect this. Otherwise, you can't apply the Newton's law of cooling anymore. There are no phase changes. So that means you won't be expecting any changes from liquid to gas or liquid to solid. Otherwise, you would have to factor in the heat of vaporization or heat of condensation, right? And then we assume that there's uniform temperature all throughout and that no radiative heat transfer happens, meaning the temperature difference between the object and the surrounding is small. And then lastly, the temperature of the surrounding is independent of the temperature of the object. So the temperature of the object could change without the surrounding changing. Please take note of these. In here, a thermometer reading 18 degrees Fahrenheit is brought into a room, the temperature of which is 70 degrees Fahrenheit. So that means the temperature inside the room is a bit more warm than the temperature outside. 1 minute later, the reading is 31 degrees Fahrenheit. You're asked to determine the temperature reading as a function of time and find the temperature reading 5 minutes after the thermometer is first brought into the room. Okay, so you are given the following data. T is in hours, and then T temperature is in degrees Fahrenheit. What was the original temperature of the thermometer?
18 degrees.
It's 18 degrees Fahrenheit. All right. It was brought into the room. So the temperature of the surrounding, which is the room, is 70 degrees Fahrenheit. And then it says here that after 1 minute, the reading of the thermometer became 31 degrees Fahrenheit. So after 1 minute, it became 31 degrees Fahrenheit. Okay. What else is being asked? Determine the temperature reading as a function of time. So you're asked to determine the temperature as a function of time. So that could be question letter A. What about question B? Find the temperature reading 5 minutes after the thermometer is first brought into the room. 5 minutes after it was first brought into the room, so you're asked T at 5. Okay, so this one is, say this is letter B. Okay, so you know that the changes in temperature is proportional to the difference in the temperature itself. So in here, we would have dt capital over d small t is K times the differences in the temperature. So this one you can use Ts or T sub 0. So let's just try to plug in what we can plug in already. So this is K, this is T minus 70. So at least there's less unknowns. So dt over T minus 70 is equal to K dt. And then we can integrate them. When you integrate, what happens to the left? This is
ln t minus 70.
ln of T minus 70. This is K T, right? Plus C. Am I correct? And then if you want to combine the C to the other side, what's going to happen is, let's just say ln of T minus 70. Let's just say, is an lnc still a constant?
Yes, sir.
Yes. So if you want, you can combine them. That's going to be ln of T minus 70 all over C is equal to KT. And then if you remove the ln, T minus 70 is equal to CE to the KT, or your working equation is actually 70 degrees Fahrenheit plus CE to the KT. So this is your general solution. Are we given any initial conditions? Yes. So that means initially, so condition number 1, the temperature when time is 0 is 18 degrees Fahrenheit. So I can say, applying that, it's going to be 18 is equal to 70 plus CE to the K at 0. What is C?
Negative 52.
Negative 52. Therefore, I can say that the working equation would be 70 minus 52 e to the KT. But still, this one is not yet acceptable because look, it's still letter K. So there is another condition. The other condition given to us is this one, that at 1 minute, the temperature is 31 degrees Fahrenheit. So let's apply that. 31 is equal to 70 minus 52 e to the K times 1 minute. Am I correct? Negative 39
Yes, sir.
e to the K. So this is 39 over 52 is equal to K. So
Negative 0.28768
6.
82.
All right. So look at K. What is K attached to?
T po.
T. What's the unit of T?
Time.
Time. So that is, what's the unit?
Hours po.
Hours. So that means, can
Over
I
hour.
say that this is over hours? Right? So it would be best that you know the units, so you know what you're dealing with. Okay. So we're able to solve for letter A? The answer for letter A is actually T is equal to 70 minus 52 e to the negative 0.287682 t. All right, so there's a question. Where did we get the negative 52? 18 minus 70 is negative 52. Take note that e to the k times 0 becomes 1. Therefore, c is just negative 52. Right? See, I'll just cancel this so you can see. This becomes 1. Right? Okay, the next question is, what is the temperature at 5 minutes? Is it time hours? Sorry.
Minutes.
It's minutes. Sorry. Thank you for raising that. This is not hours. This is minutes. This is also minutes. So this one is in minutes. So this is per minute. All right. Thank you for that. After 5 minutes, what's going to happen? So let's just plug that in. T is equal to 70 minus 52 e to the negative 0.287682 times 5.
57.66.
Roughly 58 degrees Fahrenheit. And I have a question. Do you think there will be in any way the temperature here will be equal to 70?
No po.
It could, kasi look, if time is infinity, negative times infinity is negative infinity. Am I correct? So at negative infinity, e raised to negative infinity becomes 0. So 0 times 52 is 0. So the temperature becomes 70 when time reaches infinity. The temperature here will not be above 70. That's what we can say. You understand?
Yes po, sir.
Because it can only, laws on thermodynamics, you can only have the same. You cannot exceed that. This one's quite interesting. The body of a murder victim was discovered at 11 p.m. The police doctor on call arrived at 11:30 p.m. and immediately took the temperature of the body, which was 94.6 degrees Fahrenheit. He again took the temperature after 1 hour, when it was 93.4 degrees Fahrenheit. And he noted that the room temperature was constant at 70 degrees Fahrenheit. Used Newton's law of cooling to estimate the time of death, assuming that the victim's normal body temperature was 98.6 degrees. So there's a lot given. Okay, so you're given 8:29 p.m. Okay, so let's set up our table. And I hope it's easy for you, to set up the table. T is in hours. And then temperature is in degrees Fahrenheit. Okay. Discovered at 11 p.m. On call at 11:30 p.m. Instead of hours, let's just use time first. So this is the time on top. There's a question. We're not sure if it's 1 hour because you're not sure whether when you discovered it, it was already 1 hour dead. You understand? So this is time in hours. 11 p.m., you don't know what the time is. Let's just say T. All right? And then at T hours, the temperature was what, guys? Hindi mo alam. But at T plus 0.5 hours, which is 11:30 p.m., what was the temperature daw? It is 94.6. And then it says there that, and he noted the room temperature was, he again took the temperature after 1 hour. So after 1 hour, that means the time is 12:30. Time plus, so if the time is here 11, I can say that this is 1.5. The temperature was then 93.4. He noted that the room temperature was constant. So the room temperature of the surroundings is 70 degrees Fahrenheit. And you know that when he was alive, when there was no time yet, his temperature was 98.6. This one is unknown. What his temperature then at 11 p.m. T is equal to Ts plus C e to the kt, right? So T is equal to 70 plus Ce to the kt, right? Any questions on how I got this?
Answer.
So far none? Okay. So there's a question. The Ts is the temperature of the surroundings. Yes. The surrounding temperature is 70 degrees Fahrenheit. All right? Okay. So what conditions are we given? Oh, okay. I know the initial. That the temperature at 0, so initial body temperature was 98.6 degrees Fahrenheit. So I can plug that in. 98.6 is equal to 70 plus C e to the k times 0. So with this, automatically, this one is equal to 1. All right. Therefore, I already have the equation. But then I don't know the k yet. So T is equal to 70 plus 28.6 e to the kt. All right. So maybe we can use the two equations already. So in here, condition number 1. Let's just say this is number 1. This is number 2. Using 1. The temperature is, you know that that's 94.6 is equal to 70 plus 28.6 e to the k times t plus 0.5. All right, can you please solve what's 94.6 minus 70? Am I correct? 24.6 is equal to 28.6 e to the k times t plus 0.5 using 2. 93.4 is equal to 70 plus 28.6 e to the k t plus 1.5. So 23.4 is equal to 28.6 e k t plus 1.5. All right, so it looks ugly, but what we can do probably, guys, is this. I can safely say ln of 24.6 over 28.6 is equal to k times t plus 0.5. And then this one is 23.4 over 28.6 is equal to k t plus 1.5. Can you please solve for these ln's for me?
It's negative 0.15, 0.66.
Is equal to k t plus 0.5. What about the lower one?
Negative 0.20067.
This one. All right. So I can say that using the upper one, can I say that K is actually equal to negative 0.15066 divided by T plus 0.5. K is negative 0.20067 all over T plus 1.5. Let's call this B.
0.66 over T plus 0.5.
Negative 20067
2.51.
you can see that T, look at this, T is your 11 p.m. 2.51 hours na siyang patay. So what is the actual time of death? Minus 2.51 hours. 11 minus 2.51. And then press the DMS, degrees, minutes, seconds.
8.49 po.
8.49. Please press this as DMS, degrees, minutes, seconds.
Sir, 8 hours, 29 minutes, 24
Oh.
seconds.
What's the seconds?
24.
So what time did the person die? 8:29. See? So you can actually get it up to the second. So you can be, guys, you can be forensic scientists.